Have you ever wondered how your GPS can predict your arrival time down to the minute, or how a video game knows exactly where a character should land after a jump? Well, the secret sauce behind all of it is a powerful idea from math called a function. In this explainer, we are going to pull back the curtain and demystify functions, showing you how they're literally the hidden language that describes our world. So here's the game plan. We're going to start with the absolute basics. What is a function really? Then I'll show you a super simple visual trick to spot them in the wild. After that, we'll see how you can chain them together to build something even more powerful, and finally, we'll put all that knowledge to work on a real-world problem.
All right, so let's jump right in at the very beginning and nail down the most important question of all.
It's way more than just some formula you had to memorize in school. At its heart, it's a very specific and, a very important kind of rule that explains how two things are related.
Okay, this right here, this is the golden rule. It's the one thing that a relationship must have to be called a function. Every single input, we call it an object, can only lead to one single solitary output, which we call an image. That's it. That's the whole deal. One input gets you exactly one output. No exceptions.
The best way to think about this is like a vending machine. Seriously, you press button B4. That's your input. You expect to get that specific bag of chips, your output, every time. Now, if you pressed B4 and sometimes you got chips, but other times you got a candy bar, you'd say that machine is broken, right? A function is like a perfect vending machine. It's totally predictable.
And this brings us to a really key distinction. Look over on the left. It is totally fine for different inputs to give you the same output. Think about the function x squared. You plug in -2, you get 4. You plug in 2, you also get 4. That's a many-to-one relationship, and it's perfectly okay. But look at the right. This is the big no-no. A one-to-many relationship, where one input could spit out 2 or more different answers. That breaks our golden rule.
So now that we have our core rule, let's turn it into a super handy visual tool that we can use on pretty much any graph. Turns out there's a really simple graphical trick that does all the work for us. It directly checks our rule without us having to do any complicated math at all.
It's called the vertical line test, and the logic behind it is just so clever. See, a vertical line represents a single x value, our object. So if you can draw a vertical line that hits the graph in more than one spot, it means that one input has multiple outputs. And as we just learned, that's a deal breaker. That's not a function.
And you can see it perfectly right here. A nice, smooth parabola. It passes with flying colors. No matter where you draw that vertical line, it's only going to hit the curve once. But a circle? Whoa, that fails big time. A single vertical line can slice right through it in 2 places. That means one x value has 2 different y values. So a circle is a shape, it's a relationship for sure, but it's not a function.
Okay, so we know what they are, we know how to spot them, but what happens when we start linking functions together, like dominoes?
This is where things get really interesting and really powerful. Chaining functions together lets us model processes that happen in multiple steps. It's kind of like an assembly line, right? The output from one station becomes the input for the very next one.
So let's follow a number x on its journey. First, it dives into function f, and what comes out the other side is f of x. But we're not done. That result immediately gets fed into the next function, g. The final thing that pops out at the end of the line is what we call g of f of x. It's a chain reaction. Now, I gotta be honest, the way we write this down can seem a little backwards at first. We write g of x, but the function we actually use first is f. The key is to just remember this one simple trick. You always read it from the inside out. Whatever function is snuggled up right next to the x, that's where you start.
Okay, so let's put on our detective hats for a second. Let's see how we can use these rules to actually find missing pieces of the puzzle.
All right, check out a situation like this. We know the outer function, f of x, and we know the final result of the whole assembly line, fg of x. The mystery we have to solve is, what was that inner function, g of x? Here, we can actually work forwards. We know the rule for f is just take whatever you're given and subtract 3. In this case, the thing that's being given is g of x. So f of g of x is just g of x minus 3. From there, it's just a bit of algebra to solve for g of x. But what if the outer function is the one that's missing?
Now this is a whole different ballgame. This one's a bit trickier. We know the first step in the assembly line, f of x, and we know the final product, g of x. But we have no idea what the rule for that second machine, g, is.
We can't just substitute things because we don't know what g of x looks like. We need a whole new strategy here. And this is the aha moment. This is the secret weapon. To figure out what g is, we need to get it by itself. And to do that, we have to find a way to, well, to cancel out or undo the f of x part of the equation. And the mathematical tool for undoing a function is called its inverse.
So here's how this cool trick works, step by step. First, you find the inverse of that inner function. So if f of x is add 1, its inverse, f inverse of x, is going to be subtract 1. Simple enough. Then you take that inverse and you substitute it into your composite function. And then, step 3, this is where the magic happens. The function and its inverse basically annihilate each other, they cancel out, leaving behind just the g of x you were looking for all along. It's an incredibly clever way to isolate that unknown.
Okay, so we've been playing with x's and g's and inverses, but why does any of this actually matter? Let's get out of the weeds of pure math and see how this stuff works in a real scenario.
Imagine a hot air balloon getting inflated. We've got two different pieces of information here. First, we have a function that tells us the balloon's radius based on how much time has passed. Then we have another formula that tells us its surface area based on its radius. See the chain? Time affects radius, and radius affects area. Our goal is to create one super efficient function that lets us jump straight from time to surface area without having to find the radius in between. This is a perfect job for a composite function. And boom, this is what it's all about. By building that composite function, we can just plug in a number for time, like 2 seconds, and get a direct, concrete answer for the surface area. We've basically built a mathematical shortcut that connects our starting point, time, directly to the answer we care about, surface area. So that's our deep dive into functions. The big takeaway here is that they aren't just abstract things in a textbook. They are incredibly precise tools for modeling all the predictable cause and effect relationships that make our world work, from converting currency to figuring out the physics of a rising balloon. So the real question is, what chain of events in your world could you model next?